Series resistors. For resistors in series configuration, there must be one common point or node between two resistors. The total resistance of a series configuration is the sum of the resistance levels. In equation form, if we say that there are n number of resistors connected in series, then the total resistance RT will be R1 plus R2 plus R3 plus R4 till Rn. The more resistors we add in series, the greater the resistance, no matter what their value is. The largest resistor in a series configuration will have the most impact on the total resistance. For example, if you consider this configuration, over here R1 has one node, common node or common connection with R2, and R2 has another node with R3. Thus, R1 is in series configuration with R2, R2 is in series configuration with R3. So, the total resistance RT will be R1 plus R2 plus R3, which is equal to 140 ohm. However, in this case, R1 and R2 are not connected in series because another resistor R4 has an intersection in the node between these two resistors. Example: determine the total resistance of the series connection. Note that all the resistors appearing in this network are standard values. So, let us consider this circuit diagram. Over here, R1 and R2 has one common connection. So, R1 and R2 are in series. R2 and R3 has a node. Therefore, R2 and R3 are also connected in series. R3 and R4 has one common connection or node. Thus, this is also connected in series. Hence, in between terminal A and B, the total resistance will be the summation of the resistances of R1, R2, R3 and R4. This is because all the four resistors are connected in series configuration. Hence, RT equals 20 ohm plus 220 ohm plus 1.2 kilo ohm plus 5.6 kilo ohm, which is equal to 7.04 kilo ohm. Parallel resistors. In general, two elements, branches or circuits are in parallel if they have 2 points in common. For example, in this circuit we have two resistors R1 and R2. R1 and R2 have two common points or two common nodes. Thus, R1 and R2 are in parallel configuration. In this circuit, you can see that R1 and R2 have two common points A and B. Therefore, R1 and R2 are in parallel. However, this entire configuration of R1 and R2 in parallel has one common node with R3. So, this is parallel. That is, R1 and R2 is at first parallel, and then this entire configuration is in series with R3. In the third circuit, you can see that R1 and R2 have one common point B. Therefore, R1 and R2 are in series. However, this branch AC has two common point or two common connection with R3. One over here and the other one over here. So, the branch AC is in parallel with this branch of R3. In order to determine the resistances of resistors connected in parallel, we need to apply the following equation. That is, 1 by RT equals 1 by R1 plus 1 by R2 plus 1 by R3 plus 1 by Rn if n resistors are connected in parallel. Example: find the total resistance of the configuration shown below. In this circuit, R1, R2 and R3, all these three resistors have 2 points in common. That is, at this node, R1, R2 and R3 has a common connection, and over here at this node, R1, R2 and R3 has a common connection. Therefore, the total resistance RT will be equal to 1 divided by 1 by R1 plus 1 by R2 plus 1 by R3, which is equivalent to 0.69 ohm. Convention for current flow in DC circuits. For DC circuits, in case of a source, the current flowing through the circuit will always enter from the negative terminal and comes out of the positive terminal. However, in case of a load, the current will always enter from the positive terminal and comes out of the negative terminal. In other words, for single voltage source DC circuits, conventional current flow always passes from a low potential, that is lower potential, to a high potential when passing through a voltage source. However, conventional current flow always passes from a high potential to a low potential when passing through a resistor or load. The next convention is regarding summing up of voltages. Now, consider that you have two elements, element 1 and element 2. The potential drop across element 1 is V1 and the potential drop across element 2 is V2. As usual, the positive sign represents the higher potential side and the negative sign represents the lower potential side. Well, while adding up voltages, when we move from higher potential towards the lower potential, then the particular voltage must be added. And when we move from lower potential towards higher potential, then that respective voltage must be subtracted. In this case, we are moving from higher potential towards lower potential. So, this voltage V1 must be added, that is plus V1. And in this case, we are moving from lower potential towards higher potential. Therefore, this voltage V2 must be subtracted. So, the sum of these two voltages in this case will be V1 minus V2. Voltage sources in series. It is possible to connect multiple voltage sources of different values in series combination. However, voltage sources can be placed in parallel only if they have the same voltage. More explanation regarding series and parallel circuits will be given in the next section. Voltage sources and ground. Electrical and electronic systems are grounded for reference and safety purpose. Symbol for the ground detection is this one. The ground basically means that this is supplying a potential of 0 volt. Each and every electrical circuit must have a ground, that is a node or a point which has 0 potential.